Hello everybody. So in the last module we looked at determining what our population was and then looking at how we could draw samples from our population. And this module is a continuation of that module, and you'll see more of why we're calling this inferential statistics, because what we're going to talk about in this module are three big ideas that we need to be able to take our samples and make inferences about our population. And those are degrees of freedom, determining what we call the standard error of the means, and then ultimately looking at confidence intervals. So at first this may feel like it's giving you a lot of math, but don't stress over that. I'm going to try to make it as simple and straightforward as possible. And so in looking at this, we're going to hit those three things in order and give you an example so that you understand why you need them in the order that we're going to present them, okay? So our goal here overall is to be able to draw a sample or samples from a population and make some inferences to our whole population based upon the sample data that we draw. So that's our big overall goal. So how are we going to get there? We're going to do these smaller goals. Number one, compute point estimates of a population mean, mu, and standard deviation sigma. Distinguish between the standard deviation of a sample, which is what we've been doing, and the standard error of the mean, noted as S subscript x bar, with regard to the elements of a distribution. Describe three implications of the central limit theorem. Determine the standard error of the mean from the sample data. Distinguish between point estimation and interval estimation. Use characteristics of normal curve to calculate confidence intervals for any reasonable level of confidence. And then finally translate information about confidence interval around a mean into a probability statement. And so we're going to do all that, and it's not going to be as foreign as it may sound at first here. So to get us started, let's take a scenario here. Consider that we have two research groups, and they want to look at the average ACT score in the United States. And they're acting completely independent of each other. They have different samples. Our population would be everybody who took the ACT in a given year. We assume they're looking for a year. And so what they're trying to do then is to pick up some terms from our last module. They're trying to determine the parameters of the population by looking at the statistics of the sample. So let's say that one group came up and said the national average or the national mean for ACT was 19.4, while the other group determined the national mean was 18.5. And what if I told you they were both correct? You would say, how can this be that they're correct and they're almost a point off? So we're going to look at that and understand how they can both be correct, and that there's probably more information that we don't have, but on the surface to a layperson. And you're going to give up that title once you finish this course in looking at statistics. To a layperson, they look like they're not correct, but you're going to understand why they could both be correct. So we'll examine this as we learn to compute the estimate of population parameters in this module. So we've reviewed descriptive statistics for populations up to this point, and pretty much all that we have done, we've talked about populations and samples, but we pretty much have used the population formula for this up to this point. We've looked at mean, median, mode, range, variance, and standard deviation, and this gave us all of our descriptive statistics that we needed to describe our population. We're going to use the same items in this module, but we're going to use them for samples, not our populations. And there's a slight twist that we're going to do, or tweaking of those formula, to estimate what the descriptive statistics could be for our whole population. So we're going to look at samples, use these same descriptive statistics, but twist our formula slightly, and then be able to describe our population as a whole, however we define our population. So let's take for instance here, let's say you have a principal and you're a principal, and you've been asked to find out on the number of absences for the past 5 years. Somebody wants the average number of absences you've had every day for the past 5 years. And we're going to assume that we don't have a sophisticated computer system like we do now, the student information systems that could probably pop this out for us. But in reality, we'll say that, yeah, for 5 years of 175 days each, you have 875 days of school, and you've been asked to find your average absences. Okay, so our population in this sample, or this story, is the 875 days. Okay, that's how we're going to define our population here. We could look at every day and get an exact number. Or we could take samples and get a close number that we could then infer to our whole 5 years. And so the principal chooses 269 days at random. And remember, we get this from our sample chart that we used in the last module. Within this 269 days, we know that there are going to be days where maybe the weather was bad and a lot of students stayed home. Days where there was a pep rally and a lot of students came to school. And then normal days in between. Okay, so we're trying to get all the extremes, and based upon that data chart, if we pick 269 days for a sample out of a population of 875, we should be able to pick up most of those extremes. The data showed a distribution that fit nicely into our bell curve. So remember our bell curve. We're going to look at the bell curves again in this module, but in general, we had obviously an equal number of days above and below the mean. In theory, that's going to happen. Some days had higher absences and others had lower. Any single day, in theory, could have an equal chance of being on the top or the bottom. This is considered an unbiased estimate of the population. Okay, this is a point estimate for the population mean. So our X bar in our sample mean is considered to be the same as our population mean, because we followed the rules that we established in the last module. It was a random sample, and we had the appropriate number within our sample to guess at what our population mean is. And so therefore, we're going to say that our population, or our sample mean X bar, is equal to our population mean mu. So the problem here, though, is that we know that it cannot be 100% accurate unless we looked at the whole population. Specifically when we look at variance, and follow the logic here, okay? A smaller sample is going to have less variance than a larger sample. And that's true of anything. Think of your classes. If you have a class of 10 students, the abilities within that class are going to vary less than a class of 30 students. Or if you took your student load as a whole with 140 students. When you look at 140 students, you see the abilities of all your students. Let's say you're teaching 9th grade students, or you're teaching 4th grade students. well, fourth grade you're going to be limited probably because you're probably departmentalized. But if you are teaching ninth grade students and you have a course load of 140 students, the abilities of your whole student body are going to be greater at 140 than they are if you have a class, and especially if your class are as small as 10. Okay, so that's showing you this example that the smaller our population is, the less variance there is. Okay, so if we just take samples out of our population, we know that our samples, in theory, are going to have less variance than our population as a whole. So so if we were to take 3 scores, they would have less variance than, say, 15 scores or 100 scores. Okay, so same thing I just said. In our sample, we're looking at 269 days out of 875. The variance will be for the 269 days in general less than the variance would be for the 875, simply because there are more cases to consider. We feel confident somewhat that our sample has all the extremes, but we can't be 100% confident. So what we are going to do is have to compensate for this. And how can we determine then that the variance of our sample and ultimately the standard deviation from our sample is close enough to the mean that we can make generalizations about our population? Okay, and so here's where the first of our 3 big overarching ideas comes in, and this is called degrees of freedom. So you should recognize this chart here from a previous module when we were talking about people doing sit-ups, and we were looking at things like mean, median, and mode, and range. So in here we had a sample of students from the class who could do sit-ups. The average class student could do 27 sit-ups, but in our sample of 6 we had a range of 15 to 38. And so what we did then is in the third column there where our score, this is the deviation from the mean. And so what we did is we wanted to see how far each student's actual number of sit-ups was from the mean. And so we subtracted them. And so we had some negative numbers and we had some positive numbers. And in theory, all these deviations from the mean would sum up to 0. That's important because we're going to come back to that in just a minute. So in order to figure out something to do with this, we squared all these, and that became our sum of squares. Okay, and then we divided our sum of squares by our sample size, and that gave us our variance, and then ultimately by taking the square root we got a standard deviation, so that we could get an idea of how dispersed our sample set was from the mean. So the sum of squares was the formula that we used, but we're going to look more specifically at our deviation from the mean. Okay. So the sum of squares was taken from the sum of the deviations around the mean. This sum, as we said, is always 0. So it's important to see that this is always 0. Now, why is that? So let's look at the deviation from the mean. So let's say that we have a sample with an n of 5 and a mean of 10 in our sample. We know that all deviation from the mean, when they're summed up together, the sum of the deviations has to equal 0. So we can randomly assign any number to score 1, such as 5, score 2 is 13, score 3 is 10, score 4 is 1. And our chart looks like this. In sample 1 we had a score of 5, in sample 2 we had a score of 13, in sample 3 we had a score of 10. And you can see what I did here is our mean was 10, and our deviation is on the side. So this is important to see because it doesn't matter what we put in these first scores. The only thing that matters, I could change this first one to a 4, and this would be a -6 on the end. I could change this one to a 23, and it would be 13 on the end, the deviation. What matters here is what goes in the last sample. Okay, in theory, think of this in theory. Because we know that our deviation from the means has to sum up to 0, whatever we put in all the first samples, the last one is automatically set. So when we reach score 5, x sub 5, you have no choice of this number. For example, in our set of 5 here, this number has to be 21. So that when we have 21 minus 10, we get 11. And then when we sum up all our deviations, our sum of the deviations becomes 0. So you can see that our last score has to be set. We don't have the freedom, in other words, to choose what that last score is. This is illustrative of trying to infer the scores from the sample to the population. Because we are not completely positive of all scores, we are working only with the sample. We use what is called degrees of freedom, or simply abbreviated DF. This is illustrated as n-1 when we're looking at samples. And by doing this, what we actually do is increase the variance and the standard deviation slightly when we're looking at our sample from what the actual population mean should be. And we'll see some examples of this, of how it works. But keep in mind, that's what we're trying to do, is we're trying to increase the variance and ultimately the standard deviation slightly so that we can make up for the fact that we realize we don't have all the scores. Now, this is going to cause some built-in error, and we know that, and we'll look at that and how we deal with that as well. So this is our formula for variance of the population. Sigma squared equals the sum of our x squared over n. Okay. So when we want to look at the variance for our sample, instead of the sum of squares over n, we're taking the sum of squares over n-1. So that's important to remember, because we're probably going to use that for the most part now as we look at formulating our work for the rest of the class. Keep in mind, if you're using the whole population, you would use sum of squares over n. If you're using just the sample and want to make inferences about a population, you would use sum of squares over n-1. And that n-1 is called the degrees of freedom. So when I say degrees of freedom, you automatically think n-1. So to give you an example of how this increases the variance, if our sum of squares were 100 and we had an n of 5, our variance for the population would be 100 divided by 5, this top formula, which would be 20 for our variance. But for our sample, if this were a sample and we had a sum of squares of 100 and n-5, it would be 100 divided by 5 minus 1, or 4. Our variance would be 25. Okay, so you can see that when we're looking at a sample, we increase our variance slightly and therefore increase our standard deviation, because we know that, again, there's going to be some error in choosing a sample from our population. This step compensates for the lack of viewing the entire population and the possibility that we may have some extreme scores in there. So consequently, if this is our variance, then our standard deviation, here we have the sum of squares over n for our population, sigma for our standard deviation of our sample S. We have sum of squares over n minus 1. Okay? So let's look at these population or these unbiased estimates. For our population, our mean, variance, and standard deviation, our mean is simply our average. Our variance then is our sum of squares over n, and our standard deviation is the square root of the sum of squares over n. When we're looking at our sample, our mean is the same. We said earlier that if we have an unbiased population sample, meaning we followed all those rules we established, then our population mean x bar is going to equal mu. But our variance and our standard deviation are going to change slightly because we have to change our n to n minus 1. Okay? So now, I said that we know there is some built-in error in doing this. Because what if we did capture all the extreme scores in our sample? Then when we increase our variance and increase our standard deviation, we're doing it in error. If we didn't catch the extreme scores, then it's accurate. So how do we know whether it's in error or whether it's accurate? So to do this, we turn to what is called the standard error. And this is the second big thing. So we've looked at degrees of freedom and how we use them with sample populations. Now we're going to look at how we figure in how much error there might be in our sample sizes and our sample distributions so that we can make some inferences about our population. So because we know that a sample will not capture all that we want from the population, and we're going to make estimates to our population, there will be some error in our calculations. What can we know from the sample of our population, and how confident are we that we can say the descriptive statistics of the sample match those in the population? In order to answer that, we need to understand the standard error. So let's take, for example, some hypothetical study here. So let's say our population is high school freshmen and we want to know the hours they study per week. And so in order to do this, we are going to sample some freshmen around the country. Let's say our population is the freshmen in the country as a whole. Or you could say freshmen in the state of Oklahoma. But we want to draw some random samples of freshmen and we want to question them. Okay, and so that's how you see what we're doing here. Now, let's say that our population mean was 9.25 hours a week and our population standard deviation was 3.12. We will never, in all likelihood, know what our true population mean and standard deviation are, because if you were able to find out exactly what the population mean and standard deviation were, then there would be no reason for you to get samples. The whole reason that we take samples is because we don't have the resources, whether it's financial or time or simply energy, to examine the entire population. So we know that in looking at this, that, and these are just hypothetical numbers, okay? But let's say that our population mean, mu, was 9.25 and standard deviation was 3.12. So let's say that in my studies, I did 7 samples of 25 students each. And we're going to assume that all our sample sizes are the same for now. Later on, if you go on to a PhD program or something and you're dealing with different sample sizes, you'll learn how to look at this differently. But for now, let's say that all our sample sizes are the same, and that in theory I looked at 175 students here. You can see that what I've done is I've looked at the sample mean of all of our students, and The first sample had a mean of 8.76. The second sample had a mean of 10.05. Third sample 7.98, and so on and so forth. So in summary then, what I want to show you here is that in our 7 samples of 25 students each, the mean of our samples was actually less than what we know to be our true population mean. So our sample mean was 8.99 and our population mean was 9.25. Okay, so this is an example. The reason I'm showing you this is because I want you to see that there's a little bit of error built in here. Okay, 0.26 hours, about 15 minutes a week, is how much I'm off in my sample. So how do I compensate for that so that when I make some determinations about study habits of freshman high school students, I can give some limits on what my inferences are. And to do that, again, we look at standard error. So that's just more of an example of why we need to look at standard error, because you can see from my samples that they don't exactly match the population. So let's take another example. Okay, so let's assume for the sake of illustration here we have a population of 6. We have 6 scores here. We'll call them scores. And there are 5, 6, 7, 8, 9, and 10. Okay, so we have a population of 6, and you see the value of each. We're going to take a sample from our population. They should say some, not from, not form. I think I did that a few times. We'll take a sample size of 2 from our population. Because we're working with theoretically small numbers, you'll understand the possibilities here, okay? So, in working with only 6 numbers, we can quickly determine the possible ways that we can combine these 6 numbers to get a sample size of 2. We did this from our formulas in a previous module where we looked at the combination formula. And that was using factorials, and NCR means that N is the total number of cases that we have. R is the number of trials that we want. And so we just plug in our numbers and see that we could, if we were to choose 2 random numbers out of our population of 6 for a sample, we could possibly get up to 15 samples. Okay. Now think of the number of combinations you would get if this were 875 school days. Okay. So going back to that first sample. So that's why we're using small numbers here, so you can see. So actually we can plot this out. You can see here all the possibilities of looking at me drawing 2 numbers and what the average of those 2 numbers would be. Now, if we were to look at our real set of numbers, 5, 6, 7, 8, 9, 10, you can quickly look at that and determine that our average of these numbers would be 7.5. But looking at our samples, you can see if I drew a 5 and a 6, my average would be 5.5. If I drew a 7 and 8, it would be a 7.5. But if I drew a 5 and a 9, it would be 7. Or if I drew a 9 and a 10, it would be 9.5. So based upon these samples, we can do a few things here that we've already looked at. So for number 1, we can figure probabilities. If my actual population sample is 7.5, what's the probability I'll choose that? And we can look here and see, well, I could draw a 5 and a 10, a 6 and a 9, or a 7 and 8. So 3 out of 15 would be the probability that I would do that. And we could do that for all of these. And because we have such a small group here, we can quickly add these on and look at this. And you see that what we've done is created really a bell curve. It's low on the left here of a mean of 5.5. Where it goes up, our mean is 7.5. The chances of us drawing that are 3 out of 15. That's the highest. And then it goes down to where our mean is 9.5. The chances of that are pretty low. About as the same as me drawing the two low ones to get an average of 5.5. So what this is illustrating is what we call the central limit theorem. Okay. So let me explain this here. So if I were to just have randomly drawn one number and get a mean of 5.5, that's not a great description of my population mean, because we actually know what this population mean is. If I were to draw two numbers, or two samples, let's say a 5 and a 6 and a 5 and a 9, my sample mean, if I added the 5.5 and the 7 together, you get 12.5 and then a mean of 6 1/4. It's a little bit closer to our sample, but it's not exactly our sample mean. If I were to draw a third set, let's say I even drew the other extreme, a 9 and a 10, then we could take our 5.5, 7, and 9.5 and add them together and get a mean for our three samples. And I'm getting closer now to what the overall sample of the population is of 7.5. That's what is described in central limit theorem. So this is, it gets complicated, but I'm going to break it down for you. Okay, there are three tenets here that are important. Number one, if our random samples from the population are large enough, and there is a large enough number of samples, the mean from the sample means, or the mean of the sample means, will equal the mean of the population. So you saw that when I had one sample and my mean was 5.5, it didn't equal the population. When I drew two samples, my mean went up to 6.25. If I drew three samples, and in my theoretical sample drawing, I drew the 9 and the 10, then my mean went up even higher. So what this is saying is, the more samples you have, the mean of the sample means will equal the population mean. And that just makes sense. Okay? The standard deviation of the samples, called the standard error of the mean, will be equal to the standard deviation of the population divided by the square root of n. We're going to come back to that one. Let's look at the last one. The sampling distribution of the means will be distributed as a normal curve distribution. So what 1 and 3 are saying is, 1 is saying the more samples and the larger your samples are, the more confident that we can say the mean of our samples, the average of our samples, equals the population mean. And number 3 is saying that the distribution of our sampling means will be distributed on a normal curve if we have random samples and we have enough of them. And then once we accept those two things, then we can look at number 2 and accept number 2, that the standard deviation of our sample means is equal to the standard deviation of our population divided by the square root of n, our number of samples. So let's take this and put this into practice. So if we look at the total possibilities of our population when we draw two numbers, we saw that this is true. Okay, we saw that if we look at the total possibilities, if we drew 1, we saw that we were off. If we drew 2, we saw we got a little bit closer. if we drew all the possibilities, then in reality what we did is we created the normal distribution curve that we could see. So that shows that the central limit theorem is true. Our standard error of the mean or standard deviation of our samples. Okay, this is the formula that we're going to use to figure this. And it's written as S subscript x bar, and that's read as standard error of the mean, is the standard deviation of our samples divided by the square root of n, the number of samples that we have. The standard error is dependent on how many samples, or n, that we have. The more n, the more samples we take from our population, the lower our error. So for example, if our standard deviation were 7.5, so this would be 7.5 on the top, and we sampled 7, took 7 samples, then our standard error would be 2.8347. Okay, and you can do the math. 7.5 on top divided by the square root of 7. Our standard error is 2.8347. If our sample were 25, so 7.5 divided by the square root of 25, or 5, the standard error drops to 1.5. If our sample were 500, 7.5 divided by the square root of 500, then our standard error drops all the way down to 0.3354. So the question then is, how many samples do we need from our population? Understand that the more samples you have, the lower the error is going to be. Okay, so if you had 1 sample, then your error is going to basically equal your standard deviation. But the more samples you have, you start lowering that error. Okay. So what does this look like on a normal curve? Here's what it looks like. So what you have here is this blue line is a normal curve based on 7 samples. So you see that the middle of the curve is lower. Our samples are spread out because we are trying to compensate for the fact that we don't have all the possibilities within our population. And so our sample is lower in the middle and it's flatter on the ends. When we increase our sample size to 25, and this is based on that simple idea of a sample with the standard deviation of 7.5. When we increase our sample size to 25, what happens is we see a bump in the middle of our bell curve and our ends start to pull in. When our sample is at 500 samples, we see an extreme bump in our bell curve, and in theory our ends are pulled in considerably. And what we're saying then is that we feel confident that we are catching the extremes within our sample sizes, and so therefore we can pile everything in the middle of the bell curve. So let's look at this in practice. Okay, so let's use a couple of examples of how we can use this. So let's say that we took, we're going back to our population of those 6 digits, 5, 6, 7, 8, 9, 10. We know that our sample population is 7.5. Okay, and we drew 3 samples. Sample 1, we drew a 5 and an 8 and got a mean of 6.5. Sample 2, we drew a 9 and a 5 and got a mean of 7. Sample 3, we drew a 7 and a 10 and got a mean of 8.5. Now look at my notes down here. Our sample mean is 7.33. We're treating all our samples as a whole set, not just in an individual, but as a whole set. Okay? And our sample standard deviation was 1.04. So how confident are we then that this is going to be representative of our population? So in order to do that, we have to find the standard error. And this is the formula we used on the last slide. We said our standard error was equal to the standard deviation of our samples divided by the square root of n, the number of samples we have. So our mean was 7.33. We determined our standard deviation of our samples was 1.04. So we just plugged those numbers in. 1.04 divided by the square root of 3 equals a standard error of 0.600, 0.600. And so S is our standard deviation. S subscript x bar is our standard deviation of all samples, also called our standard error. Okay, so what do we do with this now? Well, this is what we do with it. Now we can plug this into our normal curve. This statement is incorrect here. Let me fix that. And we're back. So what we've determined now from our samples is that our sample mean was 7.33, our standard deviation was 1.04, and the standard error was 0.600. And so what we can do then is look at the population error. This sigma bar is the population error. So we're going to assume that on a standard curve now, if our standard deviation of the means, and keep in mind we call it that because this is the standard deviation of the means of all the samples, is 0.600 and our average or our mean is 7.33, then we just subtract 0.600 to get one standard deviation below our mean, and then subtract 0.600 from that to get 2, and so forth. On the other side we add 0.600, and then we add 0.600 to get 2 standard deviations. And the reason we keep saying normal curve is because 68% are going to fall within within one standard deviation above or below, and then 96% will be within 2 standard deviations above and below, based upon what we said here. So looking at our set of numbers, then we can suspect that whatever sample we get, it's going to fall within this normal curve, and that it would be pretty extreme to get a sample that had a mean of 8.5 or greater. Really be extreme to get samples that had a mean of 9.13. At this point, we're saying this is more than 99.9% of our sample means should be 9 or less. And we can look at the data, and we'll look at the data in just a minute, and see that this is true. 68% of all the samples that we get should fall within 6.73 or 7.93. And again, we'll look at that and see that that is true. All right. So now what we can do is actually take this one step further and convert z-scores. Okay, remember z-scores. We're standardizing our error by converting it into z-scores. Our z-score formula was x minus x bar over the standard deviation. We're going to change it slightly, and instead of standard deviation, we're going to have x minus x bar over the standard error of the mean. Okay. For this, it becomes z equals x minus 7.33, because that was the average of our means, divided by 0.600. That's our standard deviation of the mean. And the reason we're looking at z-scores is because a while ago I just said, it's pretty unlikely we're going to draw a score above 9.13. It's just as unlikely that we'll draw a score below 5.53. And we're going to see that, in fact, that could happen, but it will be pretty rare. So what are the odds of us doing that? Well, let's look at our z-scores, and we'll use our charts that we've used in the past. So we can plot the chances then of finding an average of 5 or lower. 5 or lower. Now, if you remember, in reality, there is no chance of us drawing a 5. The lowest average that we could get was 5.5, based upon the 6 numbers we have. But let's see what the data tell us we have a chance of. This means we can plot the chances of finding an average of 5 or lower by using z-scores. So let's convert 5, drawing an average of 5 to a z-score, and then put it on that normal curve that we just looked at. So we just plug 5 into our formula up there that I wrote in green. 5 minus 7.33 over 0.600. So our numerator, 5 minus 7.33, is negative 0.233. Negative 0.233 divided by 0.600 equals negative 3.8833. Let's take that and look at the corresponding place on our chart. And what we find, if we go all the way down here to the bottom, 3.8, go over to 8, we get 0.499999. Since we're on the lower half of the curve, we would actually, you could subtract this from 0.500, or you could add 0.5000 to it and see what part of the curve is above us. But what this is telling us is that we have a 0.01% chance of ever actually drawing a 5 out of our sample. And that's true. We know that to be true because we don't have the possibility of doing that. But remember early on when we looked at the normal curve and we said that the curve never touches the line. Because it never touches the line, we're never going to say there is 100% chance that this will not happen in theory, because even though we know there's 100% chance it won't happen with this set of data, in theory we won't know the complete population. So we're going to leave it at 1/100th% chance of ever drawing a 5. Moving on, let's look at something that's a reality. What percentage can we expect to have an average of an 8 or greater? So here we can simply plug in our numbers and look. So our z-score formula again is x minus x bar over the standard error of the mean. 8 minus 7.33 over 0.600 comes out to 0.67 divided by 0.600, which equals 1.1167. So that is our z-score, 1.1167. And when we look at the chart, 1.11, it falls right here. We get 0.3665. And so because this is a positive number, we're going to add the bottom half of the chart to it. So that's 0.5000, the bottom half, to this, and it comes out to 0.8665. So our question is, what percentage can we expect to have an average of 8 or greater? So since we're looking at 8 or greater, we want to know how much is left on the chart. So we simply subtract from our whole and get 0.1335 or 13.35. So in other words, we're saying that 13% of the samples we draw will have an average of 8 or greater. Okay, so that's how you're going to take z-scores and figure your samples. This is the same thing we did when we were looking at heights, and we determined the average height of men between 5'10" and 6 foot, and how many people were taller than I am, and that kind of stuff. The only difference here is that instead of using standard deviation, we have to use the standard error of the mean to determine our z-scores. Okay? Let's look at another example. How about what low average will be had by only 15% of the people? So we have our population, we drew our samples, we want to know what's the low number that 15% or less of the people will have. Well, that's simple math. We're just going to use our same formula. If we're to go back, formula z equals x minus x bar over the standard error. Instead of looking for z, we actually can figure out z, and now what we're going to do is look for x. So what's the low average? So this is just slightly tricky, so follow me here. What low average will be had by only 15% of the people? So according to this chart, we want to find, if we're looking at 15%, we're looking at low, we're looking at the negative side. So right now it doesn't make a difference, but keep in mind the normal curve is divided in half. So we want to see, looking at the curve, looking at this curve up here, we want to see, basically, if we drew a line right here, at 15%, that means we have 35% between us and the mean. So what is the z-score that would put us where we had 35% between us and the mean, which would also tell us we had 15% below us? And so we can look at this simply by finding 0.350, the closest one to 35%. And we get a z-score of 1.04. So we're going to plug that into our z-score. And we get 1.04 equals x minus 7.33, which is our sample mean, over the standard deviation of the means, the standard error, 0.600. So then we just cross multiply, get rid of our denominator. So now we have 0.6 times negative 1.04. We said it's negative because we're only looking at the bottom half of the curve, is equal to x minus 7.33. And so now what we've got to do is isolate our x. So we add 7.33 to each side. And we come out with a 6.70 equals x. And so what we're saying then is 15% of the averages will be 6.70 or lower. Okay? So that's how you look at charts and determine from your sample size what you're doing. Okay? And how much you can make this inference to the population. So we've looked at degrees of freedom. We realize that we have error built into our samples, and so we've looked at standard error. It's probably the most complicated of these three concepts because we have to figure our sample mean and our sample standard deviation before we can look at the standard error and use that. And then once we get our standard error, we can apply that to z-scores and look at a normal curve and figure out these things like percentages and so forth. So now the question is, how confident are we that this is accurate? How confident am I that 15% of my scores will be 6.7 or lower? And this is the last piece here. We're still going to stick to our normal curve a little bit, but this is what we call confidence intervals. And statisticians use confidence intervals to give a range of possibilities due to the fact that we know we have sampling error. The best way that you see this is when you see the news, you're watching the news and they give a poll and they say so-and-so is ahead in this election 47 to 45% with an error of margin of 4%. That error of margin is reflecting the confidence interval, and it's an indication that not every voter was surveyed. And so what they have done is they have taken samples of voters, and those samples then, they've gone through all those things that we just talked about, the degrees of freedom, and creating and finding the standard error and stating what they're stating in their polls. And that plus or minus 4% is the confidence interval. So how is that done? Well, the reason we do it again is because we know there's error. So how do we do it? From our normal curve, we can assume that 68% of our population lies within one standard deviation above and below. And remember, from the central limit theorem, we said that the more samples we get and the larger our samples are, that our population mean and our sample mean are equal. Important assumption that we have to do this. In statistics, we discuss confidence intervals at the 90% level, the 95% level, and the 99% level. There are other levels, but these are the main ones that we will discuss. And we're going to concentrate on the 95% level because that's really the one you will see the most. A 95% confidence interval would include a lower limit and an upper limit to form a range within which 95% of the means of the sample in from a population would fall. So, in other words, we're going to create an upper and a lower limit, and we're going to say we're confident that 95% of the means of any samples will fall within this range. We're attempting to say another way to look at it is we're 95% confident that our sample mean contains the population parameters. So how do we do this? Well, part of it includes using the normal curve. So to get our upper limit, we take x bar plus our z-score times our standard error of the mean. And to get our lower limit, we take our x bar, our sample mean, minus the z-score times the standard error of the mean. Now you're probably about to get tired of me yelling or saying, look at the z-score, but I'm going to give you these z-scores because they're pretty straightforward on a normal curve. If we're talking a 90% confidence interval, then our z-score is 1.65. If we're talking 95%, our z-score is 1.96. And a 99% confidence interval, our z-score is 2.58. Okay? So, let us take one last example of what we're looking at. So this is how it works. Let's say we have a random sample of 36 ACT scores from your school. where 150 students took the exam. What is the confidence interval at 95% that these scores represent the entire school? Okay, that's how confidence interval works, and that's the way the question would be posed to you. What is the confidence interval at 95% that these scores represent the entire school? So what do we have to do? We can easily find the mean of our 36 scores at 22.73. So our mean, our average score of our sample is 22.73. This is a point estimate of our population mean. Okay, and we said that earlier. That's that our population mean equals our sample mean. Our variance then is the sum of squares divided by n minus 1. There's our degrees of freedom. So our variance becomes 19.29. Our standard deviation, the square root of the sum of squares over n minus 1, or the square root of our variance, equals 4.39. And now we can find our standard error. Our standard error is the standard deviation over the square root of n. And here we had one sample set of 36, but we're treating them as individuals. So our formula becomes the standard deviation 4.39, and our number of samples here, in other words, the number of individual scores we have, is 36. So 4.39 over the square root of 36 is 0.73. So our standard error is 0.73. So what do we do with that? We go to our confidence intervals. Our formula of z times the standard error at 95% confidence interval is 1.96. So 1.96 times the standard error of 0.73. For our upper limit, it comes out to 1.43. And for our lower limit, so what we do then is we add and subtract that from our mean. So our mean was 22.28 for our sample. We add and subtract the 95% confidence interval of 1.43, and we get a range of 20.85 to 23.71. What this means is that we are 95% confident that our school ACT average is between 20.85 and 23.71. And we learned this from taking a sample of 36 ACT student scores. Okay? So that's what the confidence interval is. It's telling us we're going to take our samples, and based upon a z-score of 95%, we're going to determine this range of where we are. So in summary, this is a lot of information in this module. In summary, what we have learned, based upon the previous module of defining populations and samples and how do we draw samples from populations, in this module we looked at how can we determine characteristics of the population based upon our sample. So in summary, what we did is we learned to look at a population and draw samples from that population so that we can make an inference back to the population as a whole. We take our samples and determine the means for all our samples, and then figure the variance and standard deviation using degrees of freedom. We then take all our samples and treat them as a set and determine the standard deviation or the standard error of the mean from the set of samples using the formula S subscript x bar equals standard deviation over the square root of n. Our central limit theorem tells us the larger our samples and the more samples we have, the less variance and lower standard deviation we have from the actual population. In other words, we get close to the population mean, or mu. We can use the standard error once we find it to compute z-scores and make inferences about our population. And then finally, we can use z-scores to determine how confident we are about those inferences. So that's a lot of information. It's a lot of here, there, and all around. But keep in mind those big pictures. The three things: degrees of freedom. We use that to help find the standard error because we realize that our samples are going to have error, and once we determine what our standard error is, then we can use that to create confidence intervals and make generalizations back to our population. So our goals to revisit were to compute point estimates of the population mean u and the standard deviation sigma, distinguish between the standard deviation of a sample and the standard error of the mean with regard to elements of distribution, describe three implications of the central limit theorem, determine the standard error of the mean from the sample data, distinguish between point estimation and interval estimation, use characteristics of the normal curve to calculate confidence intervals for any reasonable level of confidence, and translate information about confidence interval around a mean into a probability statement. We covered all these for the except the interval estimation. That really is looking at if you had enough samples, you could treat them somewhat like a histogram that we did very early in our course, and look at those and get some interval estimations, and they would, in theory, also look like a bell curve. Other than that, we have covered a lot of material, so take a deep breath, and you have a few small questions that deal with this information.